This week we're going to go ahead and start with one-to-one functions. So last week or the last few weeks we've been discussing functions and what functions are, putting things into functions, the domain, the range, all that happy jazz. So just as a reminder, functions have a domain and a range, input and output, where each x value, which is your domain, corresponds to exactly one output. So the idea is that you're allowed to have two different x values traced to the same y value, such as demonstrated below. So below you can see 3 and 4 are two different x values, but they map to the same y value. That's totally cool for functions. They'll pass the vertical line test. You can put things in and expect one value to come out. Well, we want to look at an extra restriction on functions, and that extra restriction is the requirement that it has to be one-to-one. What does that mean? Well, one-to-one functions say that we're going to have this requirement of functions where each x value can only have one y value, but it also means that for all y values, you can only have one x tracing to it. So one-to-one. Both can only have one attached to it. So here's an example of a one-to-one function. And notice that each x value only has one line coming out of it, and each y value only has one arrow going into it. So one-to-one. Can't have any duplicates there for y values. Now, there's two different ways to prove, there's actually more than two, but we're going to talk about two different ways to prove that a function is one-to-one. Now, the first way is the algebraic way. And what this says is to prove a function is one-to-one, you must show that f of a equals f of b leads to the result that a equals b. So essentially, if you're plugging in two different x values, the only way that the y values, which is f of a and f of b, are equal is if those two starting x values are equal themselves. So once you show that, you would show that that would be proof enough that they are one-to-one. Now, on the other hand, let's say you want to show that a function is not one-to-one. It's not one-to-one. How do we do that? Well, what we have to do is we have to use a counterexample, which is simply finding one y value that has two x values mapped to it. So it's just a counterexample that you have to find and show, hey, for this y value, I can show you that two different x values maps to it, so it's not one-to-one. I love counterexample. Those are the best. So another method to prove that it's one-to-one is to use the graphing method. Now, to prove that a graph is one-to-one, what we have to do is do the horizontal line test. So you've probably heard of the vertical line test, which tests to see if a graph is a function, just a plain old function, nothing special. But if we go this way and do a horizontal line test, we're actually testing to see if it's one-to-one. So in other words, we're testing that there's no x values that are repeated. Okay, that's what we're doing with horizontal. So essentially, you're just drawing a horizontal line and seeing if the graph, if it intercepts more than once. So let's go ahead and do both of these examples. Okay, is this function a one-to-one function? Now, I'm going to tell you right off the bat, it actually is a one-to-one function. And the reason that it's one-to-one is that this is a linear equation. The largest exponent is a 1, so it's a straight line. It is one-to-one function. If you were unsure, you could always go ahead and graph it. So I'm going to pull up GeoGebra here, because we love GeoGebra. Can't get enough of it. I know. So we're going to Okay. So let's see, what is our function? Negative 4x plus 12. Okay, so we have a beautiful graph here. So we can see it's just a linear equation, straight line. And notice that if we were to draw a horizontal line anywhere on this graph, let's actually go ahead and copy this into R. That is humongous. Okay. So it's a straight line. So if you were to, straight line, doesn't matter, it just has to be horizontal. Notice that no matter where I drag this, it only crosses the line once. This means that it has passed the horizontal line test, so it is in fact 1-to-1. So that's one way to prove that this is a 1-to-1 function. Another way is to do it algebraically. So let's go ahead and prove it algebraically. So to prove it algebraically, you're going to go ahead and let f of a equal f of b. So you're essentially saying that two y values are equal. Now we need to prove that that a and that b are in fact equal. So we're going to go ahead and replace all of the x values with a on this side, and then on the right hand side we'll take all of the x values and replace them with b. So the left-hand side becomes negative 4a plus 12, because I've replaced that x with a. The input is just changing. Same thing with f of b. Change that to b. Then we go ahead and just use our solving techniques. Subtract 12 from both sides. Cancels zeros out on both sides. So negative 4a equals negative 4b. Divide both sides by negative 4. Boom, boom. We have a equals b. So since a equals b indicates that we have shown that this function is 1-to-1, QED, we're done. Okay, great. I know in some of your other classes you've done proofs, so I'm not going to get into this too much since in this class we're going to not really do many proofs, just briefly touch on it. So we've shown that it's 1-to-1 using a graph and algebraically with a proof. So here's another function, and we're asked this question, is this a 1-to-1 function? Now, this function has a square root and it has an x squared. Generally speaking, when you have an even exponent, you're going to find that it is not 1-to-1. But we always want to graph it to double check and make sure that we're comprehending it correctly. So I'm going to go ahead and graph this function and check, is this a 1-to-1 function? So graph GeoGebra again, because it's a favorite. So in the input, we're going to put f of x equals square root, which is just SQRT. It's actually the same thing as if you were to use Excel. Excel uses SQRT as well. 25 minus x squared, close parentheses. We're going to look at that function. So it kind of looks like a half circle. And if we were to draw those straight lines, and we can actually do it right on here, just draw a straight line. I'm going to hide those. Show object. Nope. We don't want to show that object. And, oops. These aren't exactly totally straight, but just go with me here, okay? So we can see that if we do our horizontal line test, it does intersect that graph twice, right? Over here and over here, indicating that this is not a 1-to-1 function because it fails that horizontal line test. So we know that it's not a 1-to-1 function. So how do we prove that something is not a 1-to-1 function? Well, we just need to go ahead and use a counter example. Counterexample. So a counterexample is just giving two different x values that map to the same y value. So I'll do something easy, just a positive and a negative, because this graph is symmetrical if you looked at that. So if x was positive 2 and x was negative 2, we're going to find the same thing. So f of 2 equals square root of 25 minus x squared. Oops, plugging 2 in there. So f of 2 equals square root of 25 minus 4. So f of 2, positive 2, is the square root of 21, which doesn't turn out to be a pretty number. But let's go ahead and plug in negative 2 just to show that we're going to get the same answer of square root of positive 21. So 25 minus, now since this is a negative being squared, I'm going to throw that in parentheses. So this would be 25 minus 4 again, which is the same thing, square root of 21. So that indicates that both positive 2 and negative 2 result in the same y value. You could also do the proof the way we did in the last example and just show that you do run into an error, because when you square root both sides, you're going to run into the problem of having a positive and negative result when you square root both sides. So give that a try and practice those proofs, because it will come in handy later on in your mathematical journey. So good luck.